Professor Uriel Frisch. He's working in laboratory of Joseph Louis Lagrange in observatory and University Côte d'Azur in Nice.
It doesn't fit.
Say again?
No, it doesn't fit.
Okay. So, well, Uriel is very well known for his fundamental contributions to turbulence and also wave dynamics and fluid dynamics. And he contributed a lot in understanding that huge complexity that turbulence, that hidden in turbulence. In particular, I could mention his theory, multi-fractal theory, that explains, that gives explanation to the, well, better say, the vision to the intermittency phenomenon. Okay, and the turbulence remains one of the major challenges in science, and it motivated many directions in dynamical systems, in partial differential equations, in in probability theory. So this will be a topic of today's lectures. So Uriel studied at École Normale Supérieure in Paris and got PhD in 1967 from University of Paris. I think I now understood correctly that the interest in turbulence was motivated by the communication with Robert Krajcman, and Robert Krajcman himself was a former assistant of Albert Einstein. And as I understood the whole story, that the interest of Einstein to turbulence was partially related to his. This is what Greg Ink told me, that Einstein was unhappy with.
I'm not aware of any interest of Einstein in turbulence.
But this is how the Krajcman got in turbulence.
No, I mean, Einstein had the feeling that particles, the way they were studied by people doing quantum mechanics, could perhaps also be understood as singularities of the general relativity equations. So he asked Robert Krajcman to look into this matter. And to Krajcman, the equation of general relativity looked excessively formidable, and he thought that perhaps one could understand something by first studying simpler equations. So he went to the Euler and Navier-Stokes equation, believing that they might be simpler. Now we know it's the other way around. So that's how he got involved in turbulence.
Interesting. Okay. Yeah. So this part. Well, so Uriel is a member of French Academy of Sciences, and his contributions was acknowledged with a number of prizes and a number of prizes from different sides, from fluid dynamics, from geophysics, from mechanics, etc. So today we have a lecture on turbulence and also on blow-up, and Uriel promised that it will be accessible to, let's say, multidisciplinary audience, so that we can all understand what is the trouble. So thank you.
Yeah, thank you very much. Well, actually, I had been told that they wanted this to be in the spirit of what one usually calls a colloquium, which should be accessible to students, including students who are in transition between undergraduate and graduate and haven't yet completely made up their mind what they want to engage in. I don't see many of those here. Because of what I've been told, actually I've been told exactly the same thing last year when I gave an elementary lecture at the Simon Center in Stony Brook. And there were a number of such young people there around. But it was on a completely different subject. Now it so happens that I gave a lecture in the year 2000 when the millennium was being celebrated in France in many ways. And one way is that a body was set up which is what's called the University of All Wisdoms, Université de tous les Savoirs, which organized 365 lectures all over the year on all kinds of scientific subjects, usually delivered by people who were well known, but they were always asked to deliver them in such a way that reasonably educated people, not scientists, could understand them. Actually, there were always many people who attended these lectures. They were all given in Paris, and many of them were high school teachers. It gives you an idea. So the thing was prepared with that in mind. Then later, I was asked at Moscow University, this was in 2000, and I was asked to give something similar at École Polytechnique, also to people who had not yet completely started in fluid mechanics. They were floating between various subjects. And also at Moscow and Beijing University for similar reasons. So most of what I would say has no equations. It's deliberate. Just at the end, there are some rather simple equations, which I added on to be slightly more specific. So there, you will see that the only risk is not that you don't understand, it's that you understand too well. So let's start. First with the word itself. So the word turbulence, its original meaning is the disordered movement or motion of a crowd. Indeed, in Latin, turba means crowd. It's actually related to other words like troops and thorp in Old English and so on. So large number of people. Now in the Middle Ages in France, turbulence, that's the way to pronounce it in French, was used as a synonym for trouble or troubles. Actually, the word trouble and turbulence are one and the same word. They both come from Latin. One is an evolved one, and the other one is a borrowed from Latin word. And to give, as evidence that turbulence in medieval France meant something very different from what we understand by it now, I've seen about, I think it was 20 years ago, at the Polghetti Museum in Los Angeles, I saw an old manuscript, not printed, but handwritten, which had a psalm of King David, written not in Hebrew, but in French translation. What was written there, which did strike my eye, is Seigneur, délivrez-nous des turbulences, which in Portuguese would be Señor, livra-nos das turbulencias. No need to give the English. As you'd see, the meaning has evolved. I mean, the fact that we are still troubled that we haven't solved turbulence is perhaps the only common meaning. Now, to come back to turbulence as we understand it now, what's interesting is that it is part of everyday's experience. You don't need a microscope or a telescope to observe the volutes of the smoke of cigarettes, the graceful arabesques of cream poured into coffee, or the entanglement of eddies in a mountain stream. These are some drawings by Leonardo Da Vinci where you see his vision of turbulence. Now, this looks both organized and disorganized, but disorganized in a very special way. The ultimate and rather boring form of being disorganized is if you have a handful of dry sand picked up from Copacabana beach after many days without rain, and you throw it on a piece of paper, so because it's not wet, it doesn't cluster. It's boring. You get a kind of Poisson distribution of things. That's complete disorder that's not particularly interesting. This is extremely, what you see here, I need the pointer here, is of course actually highly organized. So that the fact that turbulence is a mixture of order and disorder is both, how should I say, a charming aspect, but also the reason for one of the main difficulties of turbulence, because if you can explain the disordered aspect without explaining the ordered one, then you missed something essential. This one. Now, obtaining turbulent flow, as I said, is quite simple. And as soon as you have, no, this one I will show in a moment. Yeah. As soon as something is moving through the air or through water, you will observe the phenomenon. It's also present in our blood vessels. You may not be able to observe it directly, but it can lead to trouble to your health. There is also the warning that you hear sometimes in an airplane that you should fasten your seat belt because of turbulence, and then it goes like this. Now, there is such motion in almost any place, particularly in open environments, in the atmosphere, the oceans, the stars, the whole universe, etc. And it takes different forms depending on where it takes place. For example, this one is not directly observed. It's a computer simulation of large-scale structure in the universe, but it also gives this feeling that this both organized and disorganized. These are clusters of galaxies and such things that you can observe in simulations. Now, one of the important aspects of turbulence is that it disperses things. And that can be a blessing, because if you want to eliminate pollution, the turbulence will be very efficient in doing so. But there are other cases where it's absolutely crucial. For example, in stars, there is heat released by, say, nuclear fusion. And the corresponding heat must be able to escape from the star. And that's where turbulent and convective motion plays a very important role to get it out. If we didn't have turbulence in the atmosphere and the oceans, the weather, for example, would become predictable for very, very long periods. I mean, like months. And I don't mean the ability to predict in winter that 6 months later it's going to be hotter. That's very easy. Now, let's become semi-technical, but not much. The transposition of a phenomenon known for centuries into mathematical language has started roughly 2.5 centuries ago. It was Leonhard Euler who did something in principle simple, but people had not thought about it before. He decomposed a fluid into tiny parcels of fluids and then applied the fundamental law of mechanics as described by Newton's law to each of them. And doing that, he was able to obtain an equation which is now referred to as the Euler Equation, where this is the acceleration and this is the force exerted by changes in pressure. So this was written in 1755 and published in 1757. There was a big celebration in 2007 for the 250th. Now, you may wonder where the equation really written like this, almost. There just were no vectors, so one was writing not one equation, but 3 equations, but it's such an obvious thing that you can, when you read Euler's paper, you have the feeling, if you don't know when it was written, you have a feeling it's maybe written 100 years ago, not 250. Also, the language is modern. It's not written in Latin. It is written in French. A few years earlier, he had written a paper in Latin because at that time he was working in Berlin, but before that he was working in St. Petersburg, and he still had some connection with Russia and the academy in St. Petersburg. He was even on payroll there, but he had to provide them regularly with manuscripts. And at that time in Russia, they were still using Latin when many other countries had switched to other languages, English, French, and so on. Now, the equation written by Euler lacked one phenomenon that was poorly understood in the 18th century, which is now called viscosity. Viscosity is essentially the fact that if you have 2 layers of fluids that don't have the same velocity, this is a dramatic case where they have opposite velocities, then there's a friction between these 2 layers, and the friction comes from essentially the exchange of molecular momentum, which brings momentum from one to the other. And that thing wasn't understood until the work of Navier in 1823. Actually, he understood it rather poorly because the very concept of molecules and atoms was still a bit shaky at that time. And in Navier's paper, it was assumed that the force between two molecules would depend on their relative velocity, that if they were moving apart, it would be an attractive force, and if they were moving towards each other, it would be a repulsive force. It is not true at all that the force is like that. But it's interesting that whatever you assume about the interaction of molecules, provided you have the basic conservation laws of mass, momentum, etc., you get the right result. So Navier obtained the correct equation, and all this resulted in a diffusion, a heat-like term in the equation of Euler. Then things did move on the theoretical front, also on the observational front, because people could observe all kinds of things, walk along a canal and observe all kinds of hydrodynamical marvels. But none of this was very quantitative until later in the 19th century, when Reynolds in England started doing very precise measurements on pipe flow in pipes. And he determined that there was a certain dimensionless number which played a crucial role in deciding whether the flow is nice and smooth, or now called laminar, or disorganized like this, called turbulent. The Reynolds number is obtained by dimension analysis from the Navier-Stokes equation. It is roughly an order of magnitude of the nonlinear term divided by the viscous term. So if you have a typical scale, say the diameter of the pipe d, and typical velocity v, take the product dv, divide by the viscosity. This is the kinematic viscosity, which has a dimension lv. Then you get a dimensionless number, which we now call the Reynolds number. And Reynolds found that when a certain threshold was exceeded, typically of a few thousands in Reynolds number, the flow would become massively turbulent. And if it was too low, it would be boringly laminar. So that was a very important contribution. Now, it is true that flow within a pipe is easily controlled, and that helped Reynolds in developing the first precise quantitative measurements. But if the flow is free, is around a body and not inside a pipe, it can develop all kinds of interesting structures, and if you're able to visualize them, it can be very impressive. Here is a well-known example. That is a flow around a cylinder. You see the cylinder here, it is actually there. And you visualize with smoke, and you see this thing called a Vorlex street or a Karman street. I'm sure you have seen such things. They have been studied in great detail and analyzed theoretically, but they had actually been observed many years before by Leonardo. Here is Leonardo's vision of it. You see, it is not 100% correct, but it's getting pretty close. Of course, Leonardo, who had fantastic qualitative insight in turbulence. He was the first to use the word turbulence, turbulencia, with the modern meaning. Leonardo didn't write equations, but he came very close. For example, he would observe the eddies shed behind the pillars of a bridge on the Arno River in Florence, and follow them and observe that they decayed very slowly, and point that out in his notebooks. Now, what did he mean by very slowly? Well, in modern language, we wouldn't say that an exponential decays very slowly. A power law decays very slowly. And actually, it's a fact that the energy or the amplitude of the eddies far away from where they are produced decays algebraically with the distance, and that is a consequence of the non-linearity of the equation. Had they been linear, you would get an exponential decay. So Leonardo came very close to the essence of things. Now I'm turning to another very important aspect of turbulence, which goes back to Poincaré and partially also to Hadamard. Poincaré, in his popularization, now we'd say outreach, books, which were written very clearly. They were meant for the general public. They were far easier to read than his mathematical work. He had observed that in a gas where you have molecules, the laws of collision of molecules can be very simple. In the simplest case, you just assume that they are hard balls, and you can boom, boom, okay. And then he had a thought experiment where one of the molecules would be, its velocity trajectory would be very slightly modified. Then it would bounce in a slightly different way. But at the next collision, maybe would be further away, and assuming that at each collision the change is multiplied by some factor greater than 1. After n collision, it goes like a to the n. So that's an exponential behavior. That's what we now roughly call a Lyapunov exponent. So he explained in very simple language what we now call chaos, sensitive dependence on initial conditions. And this thing was popularized by many people much after Poincaré, particularly starting in the 70s and the 80s. And the great American geophysicist Ed Lorenz became famous with his butterfly effect, where he pointed out that it's enough that one butterfly flaps a wing, that you wait long enough and it will change everything. This is represented here in a very figurative sense. What is shown here is not the real trajectory of something in our physical space, but it is motion in phase space, but at IMPA, phase space and phase space are identical. So this is without the butterfly. With the butterfly, becomes this one. The original thing is shown here in dotted line. And you see, at first they're very close to each other, but they get far apart. And what is very important is that the trajectories separate exponentially in time. So if you make a small error epsilon after time t, the error will be epsilon e to the lambda t, and if you wait long enough, it can become enormous. Let me nevertheless point out that an error with initially epsilon that becomes epsilon e to the lambda t, it still has the property that when epsilon tends to 0, the error tends to 0 at any fixed time. There are other ways in which things can become chaotic or random, which are more violent than that. For example, the spontaneous stochasticity will give you an error which does not go to 0 when epsilon goes to 0. Violent separations and things like that. So there are many different aspects to the nonlinear physics there. Some of them being studied here, of course. They have to get their hands on something here. Now, the butterfly effect, when you look at it more quantitatively and ask about the Lyapunov exponent of the atmosphere and so on, for practical purposes like weather forecast, as you have noticed, it becomes very difficult to predict the weather for more than roughly 10 days. Not the climate, the weather. Climate is a completely different business. There are nevertheless some regional variations. My meteorologist friends tell me that the predictability in the tropics is, in principle, much better than elsewhere. Whether full advantage has been taken of that here, I don't know. But there's some hope. Yeah, we'll turn to this now. Now I want to start saying something about flows that are in a violent turbulent regime. It's not called violent turbulence, it's called fully developed turbulence. In French, actually, they don't say fully, they just say developed turbulence. I don't know what you do in Portuguese if you say developed or fully developed, but okay, it's just a matter of choice. So by this one understands what is happening when you have very high Reynolds numbers. And it's not difficult to get high Reynolds numbers. In your kitchen, several thousands is really trivial. But up there in the atmosphere and the stars, you can go into the millions and the millions and beyond, much beyond. So when you have, for example, a high Reynolds number jet, turbulent jet, and you apply certain visualization techniques, you observe this kind of thing, where here you see eddy motion on many different scales. So you're tempted to say that this kind of motion has many degrees of freedom, but what do we understand by degrees of freedom? there are many possibilities. I mean, if you want to stay at the very elementary level, you say, well, okay, there are little eddies and there are medium eddies and large eddies, etc. You can start counting them. This is a bit fuzzy. Of course, if you work with function spaces and so on, you can define such concepts and you can have all kinds of theorems, and then there are many points of view, but everybody seems to agree that the higher the Reynolds number, the higher the number of degrees of freedom, however you define them. So if there are many, many degrees of freedom, are there some simple laws? Why should one ask that? Because we know that molecular motion in the air, for example, has an extremely high number of molecules, and that nevertheless brings about some very simple laws. Thermodynamics is not particularly complicated subject. And so why are there simple laws? Precisely because there are many molecules. So is it ridiculous to expect that very high Reynolds number flow should have simple laws? That's the question that we're all faced with. And then that's a very difficult one, because there's a big difference between molecular motion and turbulent motion. Molecular motion is governed by microscopic equations which are conservative. They are governed by equations, Hamilton's equation and so on, which conserve energy. And that allows you to apply all kinds of thermodynamic reasoning. Turbulence is governed by the Navier-Stokes equation or the Euler equation, and both are dissipative. Is that true? That the Navier-Stokes equation is dissipative, that's clear, because there is a viscous term there which you can think of as converting motion into heat. But the Euler equation, isn't it a conservative equation if you are not too stupid? So you take the Euler equation, you multiply by V, scalar product, and you integrate for the whole domain, assuming there are no boundaries or something simple. And you will find after 2 lines, that the time derivative of the integral of V square of the kinetic energy is 0. So that is also a conservative system? No, that's wrong. That's wrong because we work with continuous fields, not discrete molecules, and when we start looking at the details of the proof that energy is conserved, we have to be careful. Can we integrate by parts? Can we do something? And we may well not be able to do so if the solutions are not sufficiently smooth. And something which I could not have told you 18 years ago, and is one of the few subjects where these 18 years make a big difference, is the emergence of non-speculative solutions that are constructed with serious mathematical tools and which satisfy the Euler equation are dissipative. They're called weak solutions, and they are basically distributional solutions. So the functions may not be differentiable. So what do you do with terms like V grad V? Well, you take a test function, you move the derivatives over, you know, if you have studied distribution, and then you are able to make sense of this. This game, by the way, was started by Jean Leray but for the Navier-Stokes equation. So in recent years, particularly during the last 10 years, many people have been involved in constructing weak solutions, and their goal was to understand work that had been done by the great scientist Kolmogorov in 1941, and also another great scientist, Onsager, in 1949, who had conjectured that fully developed turbulence is something very similar to what we call Brownian motion. So let me explain that first. Well, you have seen a Brownian motion curve. You know that it is the same as a random walk seen from a large distance. That's a Brownian motion curve. Now, if I were to show you a record of the velocity, or one component of the velocity, in a high Reynolds number wind tunnel as a function of time, visually you wouldn't be able to distinguish it from this thing. If you have more than an eye, if you have recording instruments and are able to statistically process this, etc., you would discover one tiny difference, maybe two tiny differences. There is one property of Brownian motion that you have to modify. You know that when you perform a random walk, for this you have to be drunk, you know, and it's very difficult if you're not drunk. Then after n steps, the typical distance traveled is not order n, but order square root of n, at large n. And so it's n to the 1/2. In turbulence, it seems to be closer to n to the 1/3. That's what Kolmogorov proposed based on an energy argument. But except for that, it is quite similar to Brownian motion, or to its variant called fractional Brownian motion. So if a velocity field has variations which go like the cubic root of the distance traveled, it's clearly not smooth. It's not differentiable. Now, when you plug in such a thing into the Euler equation, the Euler equation screams unless you tame it and tell it, please be weak. And it works. And so mathematicians have spent great efforts in constructing weak solutions in recent years and proving theorems about them. I mean, not just hand waving. Last year, they achieved what they thought was a triumph. Namely, for the first time, they were able to rigorously construct solutions, weak solution of the Euler equation, that display the Kolmogorov 1941 scaling, which is more or less also what Onsager did in 1949. And then some of us, including myself, we were very naughty to them. We told them, this is not good. True turbulence is not like that. So let's touch on that slightly. Don't know if it's in here. Yeah, it's done with disgusting little animals that will help. Yeah. So, first we have to go back again in time to Jonathan Swift. That's a long time ago. He wrote the following poem. So naturalists observe a flea hath smaller fleas that on him prey, and these have smaller yet to bite them, and so proceed ad infinitum. Jonathan Swift had something other than turbulence in mind, because there are two more lines in his poems where he points out that mediocre poets behave just that way with respect to the greater ones. To just bite them and take little piece of blood out of them. And he wanted to make fun of them. But Richardson was very fond of that poem, and he wanted to transpose it to what's happening in the world of eddies. So now, instead of a big dog with fleas on it, etc., sucking blood, just imagine that's a big eddy. There's smaller eddies, and there's energy, not blood, flowing down until it reaches very tiny scales where it's dissipated into heat. That is Richardson's vision of turbulence, which is also cited explicitly. Kolmogorov in 1941, he didn't cite many people, but he did cite this one. Now, had they drawn such a picture, this is Jeremy Beck who produced this one. He's a disgusting guy. Yes. If Richardson had tried to represent this concretely, or finding perhaps this too disgusting, had shown something that exists in the real world, like this vegetable. Then Richardson would have realized that turbulence is more likely to be like another thing that he has studied a lot, which is the coast of Britain. Richardson was the first to observe that the coast of Britain is what we now call, after Mandelbrot, a fractal. Namely, that when you try measuring it, as you take smaller and smaller steps, the length increases as a power law. It's not smooth. And so Richardson worked on fractals not so named, but they didn't think of applying it to turbulence, curiously. This happened much later, and in particular, Mandelbrot was quite active in that area. And there is some misunderstanding that I want to point out here concerning self-similarity. When you see such a thing, you say, oh, each piece is like the whole thing, so this thing is self-similar. What do we understand by self-similar? Suppose I pick a point at random and magnify. It will become completely boring. In order to see the same thing, you have to select the right places. This is not mathematically self-similar. You cannot enlarge around any point as you can for a Brownian motion. You magnify Brownian motion any place, it just looks the same. It's this truly self-similar process. mathematically speaking, you take any center and then you multiply distances by lambda, and provided you multiply the displacements by square root of lambda, the statistical properties remain the same. That's the definition of self-similarity. Brownian motion is self-similar. Turbulence is not self-similar. It's fractal, even multifractal. So understanding these aspects is a very important element of the current activity, and some of the discussions which took place at a recent program and workshop that took place in Stony Brook, several of you were there, so was centered around the issue of, can one modify the recent constructions of weak solutions and replace self-similar solutions by fractal solutions or multifractal solutions? So that is a challenging problem for which there's a lot of work going on around the planet. And there's some hope that this can be achieved. But that, of course, is for the future. I hope not too distant future. Let me just mention that there have been some hopes. I don't know if they are false hopes or not. There is a problem resembling turbulence, for which you also have fractals and things like that, and the tools have been developed to understand them rigorously, mathematically. And that problem is called the passive scalar. It's a problem which has been studied in particular by Robert Crichton, about whom we spoke earlier, where you do something horrible. You assume that the turbulence is God-given and not even fractal. Some boring Gaussian statistics, but self-similar. And then you pour something into your turbulence, some cream, some blood, pollution, whatever. That is not supposed to modify the turbulent flow, but carry it along by it. And then you want to analyze what this thing is doing. And it's been shown that it's not self-similar. It is fractal, even multifractal in a suitable sense, and you can investigate its statistical scaling properties by rigorous methods and obtain non-trivial results, etc. You can also do numerical simulations. These simulations were done by some of the people who were also heavily involved in theory. I mean, there's Massimo Vergassola and others. Beautiful things. This is not clouds in the sky. So the breakthrough there happened in the middle of the 90s, around 95. Tools borrowed from quantum field theory allowed people to understand these fractal characters in a systematic way. And then, of course, they were all excited and hoped that the next victim would be turbulence. But this problem called the passive scalar is a linear one. Turbulence is non-linear. So far, it has resisted. Although there's, at the qualitative level, there's some hope that things will be not too different. But let me finish with what I promised, namely the blow-up, which is another aspect of turbulent fluid dynamics, which is quite mysterious. You see, mathematicians, when they work with partial differential equation, particularly those that have a d by dt in them, like the Euler or Navier-Stokes equation, they like to know if the problem is well posed, if it has solution in good function spaces for some time, forever, or so, such questions. Such questions were, of course, not asked at the time of Euler and Navier. You had to wait much later, people like Hadamard, Poincaré, and so on. And when it comes to hydrodynamics, the first theorems having to do with, let's call the well-posedness of the equation of hydrodynamics were proved in the 20s. Liechtenstein in Germany, and later Leray for the Navier-Stokes equation, and many more, including some floating around. So what we still don't know at this time, if the Euler and the Navier-Stokes equation in 3 dimensions are well-posed problem when we take sufficiently smooth initial data. Do they stay smooth forever, or does something very bad happen? Let me give you a lousy argument indicating that perhaps something very bad happens. So this is really hand-waving. You start with an equation that was first written by Helmholtz, which is just obtained by taking the curl of the Euler equation, and omega denotes the vorticity, the curl of the velocity. I'm sure you have seen this equation. It tells you that the Lagrangian derivative, the omega, is omega grad u. That is, physically it means that the vorticity is transported and stretched or squeezed by velocity gradients. Mathematically, actually, it's an expression of the vorticity being Lie advected. But of course, you have to know what one understands by Lie advection, which is not for the audience I had in the year 2000. Now let's cheat horribly. Observing that the vorticity, the curl of u is just a bunch of components of the gradient of u. The gradient of u is a tensor, 3 by 3, and there are certain components that give you the vorticity. So this is the same kind of animal. So we cheat horribly, and we treat this as omega squared. So we get that the Lagrangian derivative of omega is omega squared. That we can integrate, and boom, if omega starts positive, it explodes in a finite time, a time which is just the inverse of the value it had initially. It's a completely trivial differential equation to solve. So this is telling you that if you have something moving with an acceleration which is proportional to the square of the velocity, then it will reach infinite velocity in a finite time. This is the same thing, yes. But is this really taking place? Now the paradox is that the best mathematical estimates that have been obtained so far over many, many, many years in 3 dimensions, they can't do better than this with an inequality here, less than, which guarantees that things will be nice for a finite time. But it may well be that they are nice forever, because there are mechanisms that are quite subtle, which tend to reduce nonlinearity or make them less dangerous than what one assumes here. This is the subject of nonlinear depletion, which would require several hours of lecturing, but it is something that's not ruled out. It is not safe at the moment to conjecture that the solutions of the three-dimensional Euler equation blow up in finite time. And some people who are floating around this room have even shown on an Euler-like equation that it may blow up in a finite time in such a way that no simple numerical experiment will ever tell you. So then, of course, and the lunch discussion was worse than that. We discussed the undecidability of blow-up, which is, I mean, if blow-up is proven undecidable, you better stop working on blow-up. We don't know, but it is for people who are slightly perverted, and I'm sure there are plenty at IMPA, proving something like the undecidability of blow-up is, I'm sure it gives some form of pleasure. I don't know if it would be very useful for industry. I guess I have reached the end. No, there are a few words I wanted to tell you here. Yes, this little paragraph. So I just wanted to emphasize that turbulence has a very special status in contemporary physics. It is often considered as one of the big open issues of physics, but unlike other frontier problems of physics, the phenomena in which one is interested in turbulence are neither in the infinitely small nor in general in the infinitely large. These phenomena are perfectly well described by Newtonian mechanics without any need to have recourse to quantum physics or to relativistic mechanics, that is, to the modern ideas of physics on space, time, and matter. As you can see, classical physics, that is the one taught in high school, still has some great mysteries. Yeah, so that's worth pointing out, that you don't necessarily have to go to exotic forms of physics for things to be interesting. I'm